hello. I hope you have enjoyed lunch. One question, maybe a short question at the beginning. How many of you have come by car here today or yesterday? So nearly more half of it. So did I today, and I used my GPS system. GPS system here has been in my mobile phone, and I've been really quick today. I've had to do 300 kilometers to go. And my GPS system, I already checked it before entering the car. So I decided, okay, can I have a small talk with my son before leaving, because I have plenty of time. I get the confirmation in between that I'm still on the shortest track and on the fastest track. I've been traveled around traffic jams today, so quite normal, I would say, in the meantime of today's technology. In steel plant, we sometimes do our business still using a roadmap and a compass. So we get a destination, looking where is it on our roadmap. We look for and we make a guess, we make a discussion. Where might be the fastest and the shortest track? Is it worth it to take the shortest track? Is it better to take a roundabout to be quicker? This is not necessarily bad. So sometimes you get the shortest and the quickest way by this way either. So at least as soon as you have experienced guys, you have more than one maybe. So this is a possibility which works. As soon as you don't want to have separate destinations in a short period of time, as soon as you want to have different destinations, that destinations are maybe changing, then it's getting a little bit time consuming. And this is how steel industry works like with this roadmap. And we want to present you how we in the past month and the past years developed, let's say, a GPS system for a steel plant. That's the thing we want to talk about. So maybe at first a quick view of what we are doing in Hamburg. So Hamburg is an electric steel plant with an electric arc furnace as the core melting device and the core production device. And we have two main raw materials which we are using. We have the only direct reduction plants, the only Midrex plants up to now in West Europe. Maybe this is changing during the next years, who knows. So we are producing our own direct reduced iron, sponge iron, and second is scrap. So both of it more or less half to half. Both of them are coming together to the electric arc furnace, been melted to molten steel, is prepared in the ladle furnace. Alloys are coming to it, and so on. We are adjusting temperature, we are adjusting chemical specification in the ladle furnaces, and then we are casting billets. Billets are stored in the billet yard, and most of them afterwards been produced and processed to wire rod. This is our job. So, and for sure, our job as engineers is to do this process as smooth and as effective as possible. And we have always, or in most cases, we have three goals concerning the process. We have skipped here a fourth, a very important goal. This is the safety, but this is not the topic of today. So the goal in terms of process effectivity and process quality is first the quality of steel for sure. You have to be at lowest cost possible, and you want to have the highest productivity as possible. And all these three goals might be competing. It's not always in the same direction. So, and the challenge we are facing is some of the influences like the scrap, like the iron ore, like the availability of energy nowadays. The price of energy is unpredictable, and there are high variations. So we have to adjust our destinations like on the roadmap. So, and how we are doing this at the moment, we are doing this by technologies like human experiences, like physical reasoning. We have, and I'm working in steel industry for nearly 20 years now. We are working with models. These models are basing on energy balances, on mass balances, on measurements, on statistics, and so on and so on. But nowadays, actually, we haven't done it so far to really be precise and reliable in predicting the electric arc furnace process in terms of temperature and so on, and in terms of scrap input and quality. So this is at the end our daily business. And for sure, due to these challenges and goals, there are several points where artificial intelligence could step in. So because it seems a quite lean process, but we are producing during 1 year, we are producing more than 400 different steel grades, several steel grades a day. We are managing more than 10 recipes at one time, and these recipes for the steel grades are changing on more or less a weekly basis. So at the end, there are several roads and optimization options on our roadmap, on our daily roadmap, where we can maybe take shortcuts or miss shortcuts. So this is at the end what we are doing, and today we want to talk about the point of scrap, where we are working with artificial intelligence in the meantime. So let's look a little bit what is the goal and the challenge in between when you're looking at the scrap process. So for sure, the goal in terms of quality is you have to meet the specification. So what you are melting, you have to know you are melting a mix of, let's say, 10 different scrap types coming with a variation of specification, coming with different specifications in terms of impurities and so on and so on. So you have to select a recipe which is fitting to the specification you want to have. For sure, you don't want to spend that much money for this, because this is what we are making our revenue of, our earnings of, and especially nowadays where we have a split between selling prices and buying prices, this is more crucial than ever before, I would say. And at the end, for sure, the third goal, it's quite easy. It has to be a meltable and a processable mix. It's not possible, or it's not recommendable at the end to have only one scrap type, and you put all this in. Maybe it's the cheapest one. Doesn't make sense. So at the end, you have to balance all these three goals with the challenges I've already spoken about. So we have varying, very high fluctuation of prices. You have to have a high fluctuation of selling prices. In the meantime, I mentioned it already, you have variations in availability and price of energy, and like electric energy or even gas. So, and this we are doing, this roadmap, we are, as I mentioned, we are doing this in the meantime nearly several times a week. So anybody is, so the guy in charge is going to say, okay, I have these scraps available, I know what is coming in, I know what I have to produce. Let's see how we can mix this in the most effective way. And this is quite time consuming, and like on the road, you're not always taking the fastest and selecting the fastest and most effective way to go. So that's at the end the point where the artificial intelligence steps in.
Thanks. Yeah, thanks for that. So what would then, we've just seen kind of how important the scrap-related decisions are then. So the two key decisions being what scrap to procure, and then how to mix that scrap and put it into the furnace each heat, right? The recipes, as we like to call them. What would the ideal solution be for those two scrap decisions that you have to make? What would be the ideal solution for those two things? Well, first of all, needs to be a unified solution, because the procurement decision and the decision about what recipes to put in the furnace, they're fundamentally connected. Because, when you procure stuff, you shouldn't just be procuring materials based on what is the cheapest or what is the most available, but fundamentally you need to procure stuff that's going to be the most value in use, as we say. It's the most valuable to the steel plant when it gets put in the furnace. And similarly, when you make the recipes to put in the furnace, you have to do that from the material that is available to procure. So you need fundamentally a unified solution. You need users from procurement and you need users from the steel plant that use one solution to decide what recipes to put in the furnace and what to buy from the market. So that's the key thing that an optimal solution would have. The second thing it would have is, as discussed, it would optimize for value in use. And that's just the goal that we've already talked about. It would optimize for the cost of liquid steel, not just raw material cost, the quality of the product, and the productivity. So you need a unified solution to help you to decide what to procure, what recipes to put in the furnace, and that unified solution needs to be optimizing those decisions in order to achieve this complex goal. And finally, it needs to do that in a predictable and consistent way, right? So ideally what you need to do is you need to predict, what the goal is going to be, or like how the goal is going to turn out, how well you're going to achieve it when you're making these decisions, despite all the complicated dynamical variations that were mentioned, like how each month the prices change or the availability changes or something. So that's what we've done. We call the solution Scrap Chef. Here he is. He's a co-pilot. Well, this is an illustration of him. He's kind of an AI co-pilot for your procurement and for deciding what to charge into the furnace. He's an AI co-pilot that figures out what to procure and what to charge based on this goal here, based on this holistic goal. And it does so by doing what we said. It predicts how the process will turn out. It predicts how the quality of the steel will be. It predicts the cost of making the steel, evaluates all the different scenarios and says, hey, this is the best thing to buy, and hey, this is the best thing to put in the furnace at this particular moment. So you can just think of it like a magical box where procurement puts in the availability and the prices of the scrap. That's what they enter. The steel plant enters what they need to produce, what steel they need to produce, and the magic box puts out, this is what the procurement should buy, in his opinion, and this is what the steel plant should put into the furnace. So it outputs recipes and a shopping list, basically, from the requirements provided. Of course, this fits in with the aforementioned GPS analogy, is it's kind of really a predictive solution, saying, oh, this is where you are, this is where you need to get to, this is where you are, the material available, the production plan, etc. And based on some predictions, this is the best way we think you could possibly do it. How have we managed to do this exactly? Normally if I say this to someone that works in steel, they say, yeah, but how do you really kind of do that? Do you do it based on how do you know about the scrap so that you can predict the product quality and stuff like that? Where's that actually coming from? So I'm just going to take a little detour into AI to explain how we do this with a really silly example. So imagine you want to make a computer program that looks at images and tells me if apples or oranges are in the images, right? There's two ways you can do this. The traditional approach would be that you would use handcrafted rules. So you would say like, oh, if there's lots of red in the image, it's more likely to be an apple. Or if it's really round, it's more likely to be an orange, or something like that. And obviously, that's how image recognition used to work when you made image recognition software. The problem with that, as you can imagine, is it's really hard to write down all the rules. And then after you have written down all the rules, there's always an exception. There's always like an annoying, there's a pair or whatever. Oh my God, it all doesn't work anymore. You have to start again. So this is the old way of doing it. Now, what AI basically is, as I mentioned yesterday in the panel, is instead of using manual handwritten rules, you write some software that basically learns from experience. So you provide it a bunch of examples, you provide it all these pictures of apples and oranges, and you say, this is apples, this is oranges, and it just sort of figures out the rules for itself. And in practice, it turns out that can do a way better job of the handwritten approach. Now, this is obviously analogous to the situation we've got in a steel plant, the apples and oranges. When you're making an algorithm like this, you're basically breaking the picture up here, the picture of apples, into all the pixels. Each pixel is a bunch of numbers that says how much red, green, and blue it is. And you're basically feeding that into the algorithm and then saying this is an apple or an orange, and it's learning to associate those two things. You can look at the data in a steel plant, like how much, let's say, energy the EAF used, or like some information about what scrap was procured, or what scrap was put into the furnace. In this analogy, of course, like the energy used by the EAF would be labeling a recipe, an apple or an orange, and the pixels would be what scrap did we put in, for example. So we use just the same approach, basically. We're sort of doing image recognition, but on the steel plant process. And that is, in a nutshell, how we're able to take a procurement decision or take a recipe, and based on that, predict how the product will turn out, how the process will behave, evaluate all the scenarios predictively, and then choose the best one, right? Same way that Google Maps is working as well. So just as a quick summary, a couple of the features, long-term and short-term optimization. So of course, we're doing this, it's a super dynamic problem, and you fundamentally have to do the optimization over and over and update your point of view. So we do it with a long-term perspective, plan the procurement and the recipes, and then we optimize again, often with a short-term perspective, and adjust the plan based on the actual operational realities. An example of the stuff we predict is the impurities, of course. So you take like a copper measurement, or you take like a tin measurement in the process, and we predict how that value is going to be. Guidance for scrap loading. So we do consider all of the practical complications with actually putting the scrap in the furnace. This is not like some protected project that only like the engineers and managers use. This is we kind of do it all in a way where the output is not just the recipes, but it's also how you should sensibly put the recipes in the basket, how to layer it so that there's no problems and stuff like that. And guidance from planned situations, like you can nudge the scrap chef to give you some help if something happens that isn't going according to plan, and it'll figure out what to do. Which is a common situation, of course, in real life manufacturing. How we did it, let me just go back one slide there. So how we did it, strategies and tactics for AI and steelmaking. So yesterday, someone asked me the question, like, how do you actually get tangible results when you do AI in these kind of situations? Because like it's actually hard, right, to in a really practical situation get something that works really well. We've got a few strategies and tactics that we've learned over the last couple of years together. That are like, not necessarily often discussed. These are very specific things that you can actually do in this type of project that's going to make a really big difference, I think. Like, honestly. Here's the team. Here's some of our engineers in Hamburg preparing to go on the night shift in the plant, because the first point here, how we did it, is like real location, real thing. This is the old Toyota thing, but we really believe in this. Like the AI people have to go physically to the problem and be there as much as possible. So like now, obviously, like remote work is a big thing, and remote work is especially a big thing for like digital teams, for programmers and stuff like that. We think, at least if you're doing AI in like a proper, real, physical problem, you've got to like physically be there. So we go all the time, and we just hang out. We're actually annoying. I mean, we literally live in the steel plant, and everybody that works in our company has to spend as much time as possible in the steel plant, even if there's no reason to, even if there's no problem. You have to be there, and you have to experience the whole thing, and you have to just sit there for hours on end and get a feel for it. Second thing, single-threaded owner. This is like the trendy name for Amazon give to this concept, but what it basically means is, for a site, like in Hamburg, we have one person that's really singularly responsible for the success in Hamburg at any one time, and they are an interdisciplinary person. So, for example, there'll be an engineer who knows AI, knows software development, knows steelmaking, and is capable of thinking about the product and everything. And even if they're not the most senior person in the company, they're like, it's their brainchild. And whatever they says kind of goes, and there's no part of the project that they're not responsible for. And they can commission the rest of the company to do, even like people more senior than them, to do stuff. So they can just call me up and be like, hey, you know, there's something that I can't really do, but you can probably do, can you come and do it? And like, they're the boss, basically. So they don't do all the work, but they're like the boss of the project. And they have to be a super interdisciplinary person, which obviously takes us a long time, takes like a year to get somebody to be like that. The third thing is, and obviously these combine, like real location, real thing, so it's the boss is always a person that stood there, like by definition. If you're not stood there, your opinion doesn't really count. And then the third thing is do the most useful thing now. So we're not super big. We obviously have a vision for the product, a long-term vision and everything like that, but we're not super big on like carefully planned out roadmaps that were maybe developed, you know, in a meeting somewhere. What we think you should do is like, if you're stood there, and if you're an interdisciplinary person, and if you have the best understanding of the problem, and you have all the relevant domain expertise, you should just do the most useful thing for the customer right now. And if that's slightly different to what's on the roadmap, then the roadmap doesn't really count. Like, you should just do the most useful thing. So that's our three kind of guiding principles.
And I want to add one point, because to me this is as the operator then with this simulation, it's the most valuable thing, because you have to keep it simple. So AI is a complex thing, steelmaking is a complex thing, and at first sight, where we have developed our previous AI model for the temperature prediction of the EAF. At one time, a friend of mine comes to me and congratulates me for being a front runner for implementation of AI in steel industry. And I say, ooh. But this AI simulation in this model, what we have is simply drawing some colorful, nice lines on a monitor. Not more, not less. So where is really the value? If this is the value and we are the front runner for AI, then I have my doubt. So at first step, we really took all this complexity and followed the engineering dream. So I want to have everything on one side. I want all information on one monitor, which is an engineer's dream and an operator's nightmare. So at the end, really the value that we are able to reduce temperature of the steel by 10 Kelvin, that we are able to reduce 5% of our cost for input material and scrap. This is only possible because we have to reduce the complexity. The operator gets one number, it's the temperature, and he gets a second information, which is the seconds, the seconds for tapping the heat. All the rest is reduced, and this is at the end what is, in our view, in my view, is rising and really creating the value at the end. So, but we are still at the beginning, I would say. So, my first doubts, what is the real value of artificial intelligence, is already thrown away. I guess that artificial intelligence is key and the decisive thing for if you want to be competitive in the future of the steel plant. So, if you want to be energy and material and cost efficient in future, there's no way to go without artificial intelligence, and we have several ideas where we want to implement it and deploy it even further and roll it out. So, future for us is a chance. There's always a different way, and we have to decide how we want to look at it. We think we are the brave ones. Thank you.
Thank you very much, Ansgar. Thank you, Tom, for this inspiring presentation. And I really like the summary at the end. If you want to be a competitive steel plant in the future, you need to get onto AI and keep working on these topics, because this is where the future lies. We have time for some questions for Ansgar and Tom.
Hi, Tom, we already talked, and Ansgar, nice to see this presentation and see what ArcelorMittal is doing. I think my question goes to, yeah, you're optimizing a process, but you're also putting together multiple departments, right?
Yes.
Planning and procurement, and I see it because I've worked from this industry before. Usually planning, they are doing their own thing, sort of saying. Like they have their own processes, they have their own system, their own models, and it's usually very hard perhaps to convince them, okay, now you have a system that will make your job better or perhaps substitute your job in a way. I don't think that's the case. You need still the expertise of a person. What would you say to them when you show them this? It's like, what would be like the convincing factor to say, hey, instead of doing what you're doing, try using this?
Honestly, we haven't had these difficulties in Hamburg. We are a small company, so we have 500 people, and then at the end we are from the first days of our existing, we are more or less like a family. So there's nothing really we have to convince anybody. So, but at the end, for sure, you have, in my view, you have it's about advantages and really the benefits everybody has, and everybody has a benefit. If we stay with the example of the scrap recipe we're doing and scrap purchasing, it's not only my manager for the scrapyard who's spending several hours per week on adjusting recipes. It's the purchasing guy for the scrap as well, and so on and so on. And we are and the controlling. Who has to predict the cost for each quality, and so on and so on. So, at least in this case, the benefits are that obvious that everybody is bringing in his efforts and his experience to rise this to success.
There's one question over there. If you can bring the microphone, please.
Hello, thank you for this insightful presentation. I really liked how you emphasized the fact that without actually turning it into operational reality, AI doesn't really bring the value. So my question is, has there been a time, or I assume there has, where the results were very surprising to you, where you, from an operational standpoint, might have said, no, that can't be right?
At the beginning, yes. So yes, we were a little bit surprised about the potential which we have seen in the scrap recipes. So because my first impression was, hey, I'm doing this for 10 years, and you are telling me I'm wasting 5%. So come on. So, but yes, sometimes we have to adjust. So sometimes the first feeling that it's too good to be true might be true, that it's too good to be true. But yes, at the end, I would say, especially concerning the potential of the scrap input, it's surprising, yes.
Okay. I have a question too. Congratulations, you both, for the presentation. In steel production has the very hard pressure for production, to achieve the production, but you must be very assertive also. My question is, how do you prevent the models to do something really unexpected, something that could be even dangerous for the furnaces in the production line?
It's like the GPS system in your car. If you are going into the River Elbe with your car, you might guess there is something wrong. So maybe you should take the bridge which is next to it. so the best simulation is nothing without the user. So for sure, we have experienced people, and only because it's quicker, yeah, we have time to check it. Let's say it like this. For sure, we have experienced people who are preventing us to do stupid things.
Okay, I think we have time for one or two more questions.
Yeah, thank you for the very insightful presentation. A very simple question. What is the business impact that you have been able to measure? Is there any numbers out already?
I've already pointed out some numbers. With the model of for temperature prediction, we are aiming for decreasing 10 Kelvin of our tapping temperature, and potential. In our case, it's always depending on the complexity and what you are doing. So as soon as you're always doing the same, like there are steel plants who are producing more or less one or two different grades with all the time the same recipe. Complexity is low and potential is low at the same time, I would say. So in our case, since we have a very complex process, very different qualities, I would say 5% of input cost for the scrap is, at least in our case, our potential. So at the end, everybody who is making steel has to think about what is this in euro per ton.
Thank you.
The scrap suppliers are not happy about that, I can see. Okay, maybe one final question.
Thank you very much for your presentations. Being open-minded to the changes, we are mostly discussing the advantages, the benefits of AI. But let me ask, what are the key challenges and problems the steel companies should be ready for using artificial intelligence?
At the end, I know since I'm responsible for the production, I would say for sure it's the challenge is to get, like you have already questioned or asked, it's to get valid and useful results out of it. You have to, and this is, it's not the first result which is the right one. And this is for sure, if you are implementing this, it's the most challenging thing to assess, okay, which rules or guidelines I have to set to really rely on the model and let it run. Otherwise, it's running into, it's guiding you into the River Elbe, so that you don't want that. And this, at the end, is the challenge, to really to be as close as necessary, but as wide as possible to really get the potential. And this is, at the end, it's something of which you have daily, on a more or less daily adjustment.
Thank you very much for this inspiring presentation about artificial intelligence, really in use, generating tangible results. And if we yesterday heard about the importance of creating positive business cases, this I think is a very positive result that has come out of this project. So big applause for Ansgar and Tom.